Thank you for joining and watching this presentation. I am Changyan, a software engineer and leading the Extended View system. In this session, we are going to present two camera features. One is the Extended View system, as known as EVS. That is, Android Automotive OS service helps you to access various video streams available on the vehicle. Another is Surround View. That is a new service we proudly introduced in Android 11 to help you build applications to enhance the driver's awareness of their surroundings. Let's start with the Extended View system. We introduced Extended View System EVS in 2017 as the only camera API available in Android Automotive OS. This service was designed to be simpler to maintain, available earlier than Android Framework, and easier to extend to implement camera or vision automotive applications that employ one or more camera devices. In the previous release, Android 10, we were focused to improve the robustness of the service. More test cases were added to the vendor test suite to validate EVS APIs and hard implementations from the vendors. Also, we implemented a few CDD requirements to standardize EVS experience on Android Automotive device implementations. We have been working with our partners closely last year to understand their demands and, as a result, introduce new features to reflect them in Android 11. The first new feature is the event notification. In Android 10, EVS video stream provides only the imagery data and therefore does not provide any other channel to notify the clients any streaming events or incidents. Because this constrains the behavior of the clients, we introduce a new callback interface. The clients can implement this interface to listen notifications from EVS Manager and or EVS hard implementations. Example events are start and stop video stream, or streaming error, like timeout and the parameter changes. The notification packet has also 16-byte payload, and the vendors can put additional information to help the clients handle events properly. Many camera and vision applications for the vehicle require more than the imagery data to implement their services properly. One well-known example may be the camera calibration data that is required to project the real-world object into the 2D image plane. In Android 10, the client developers must get necessary information by themselves and store them locally in their own locations. We would like to enhance this situation by introducing the camera metadata, so allow the clients to retrieve, for example, the calibration data from the device descriptor. Also, we have added a metadata field to this frame, to the frame descriptor. This new field is opaque to EVS Manager, and the vendors can put any additional data, for example, the coordinate of the object for the client. The next is a new API to program camera parameters such as the brightness and the color saturation. From Android 11, EVS video stream is not the one-way stream any longer, and the clients can program parameters to control the underlying camera devices. Because the multiple clients can be on the same EVS video stream, this feature also introduces the concept of the primary device owner. The client must acquire the primary ownership to be able to program parameters. EVS service prioritizes the clients with the display ownership and notifies if the primary client loses their privileges. From the partners, we learned that many use cases need more than one camera device, but it is not easy to do with the EVS because many things have to be done in applications. We would like to enhance this multi-camera service development experience by introducing the logical camera, that is a group of one or more physical camera devices. The application can use the logical camera device just like the single physical camera device to obtain the imagery data from all member camera devices. To have this feature, by the way, there is one requirement. The device implementation must support the Android synchronization framework. And similar to camera hub, the logical camera device must declare the logical camera capability in its metadata. While most Android mobile devices have a single screen, more than one screens are available on many Android Automotive OS device implementations. We plan to leverage this difference to optimize the user experiences and, as the very first step, introduce the new interface to query display devices available to EVS clients and open one of them as the destination. The last new feature we introduced today is to enhance the development experience. In the current version, Android local messages are the only way to understand the current status of EVS services, and the developers must parse the messages manually to diagnose the issues. With the streaming events notification introduced earlier, we also provide the method to monitor and dump the current status of the services via as a high utility. I'm going to demonstrate a few examples to show you how to use this feature. In this demo, we use the virtual video test driver, Vivid. Let me load the module and you now see that video 3 has been created by the Vivid driver. Now, I'm starting the EVS service by setting this persistent property and start the EVS application. EVS provides a few debugging information via ls debugging commands. This shows all the options currently available. At the beginning, you can list the camera and display devices which are available to the EVS services and dump their current status. For example, display, you can see the size and refresh rate and also rotation as well. And for the camera, you have the how many frames have been received and dropped and processed by the clients. And also it gives you the average latency of the round trip of the frames. And by default, we collect the few statistics and store their snapshot at regular time interval at 10 seconds. So you can see how, if there's any fluctuation in the services, you can notice, detect it by by checking this collected statistics. And also the developer can start the collection with the custom interval and generate the report. For example, this command collect the statistics at every 1.5 seconds and during the 100 seconds. And you can stop at any time after you start the collection, and it generates the same report we just see before. Hope this feature helps you to understand the EVS usages and diagnose the problems you possibly has while you are developing the EVS services. And we have one more thing. When we analyze the automotive camera use cases, we find that common patterns, and therefore would like to introduce the support library that helps you to make the camera service easier by providing use case-based, easy-to-use API surface. For example, you can create the camera preview application simply by creating the display use case and requesting to start the video stream. These are all what we prepared for Android 11. Hope these new features help you to build a great product. For the partners who worked on the previous version, we will publish EVS 1.1 migration guide at source.android.com to help you with smooth migration. Also, the sample EVS application, reference EVS hard implementation, and EVS driver implementations are available at these locations. Please take a look and try. Thank you for listening to my presentation today, and please enjoy our next interesting topic, the surround view.
Cool. Thanks, Jongyong, for introducing all the new features in EVS. All these features are a great build towards the new feature that we're introducing, and that is surround view. I'm Tanmay. I'll be introducing this feature, and we'll be deep diving into all the details that we are offering for this. So first thing, what are the things, how we're going about this presentation is going to be first, I'll give an introduction of just what surround view is and what kind of solution we are presenting in Android Automotive OS for this. Next, we'll go into the HAL, that's the hardware abstraction layer that we have defined and introduced in Android 11. We also will offer an implementation for that HAL, and we will go into the details of that as well. And then finally, we'll look at what are the upcoming features that we'll be looking at. So I'll get into the introduction next. So surround view is a very popular feature now, almost available in all new cars now. Basically, the idea is to give the users a sense of safety and assistance to the drivers while driving or parking. It involves using these cameras installed all around the car, stitching them and presenting them to the user in a way that is helpful. And the goal of Automotive OS is to forward that and even improve on what current offerings there are. So basically, the surround view is going to be a whole 360 view of everything around the car. And we will be introducing new APIs and algorithms and features to enable this within Automotive OS. One of the key things that we do is we leverage all the great work that EVS already has built, and we build another layer on top of that for applications to use. And few things that we've kept in mind while designing this is to make it customizable and usable for any applications and OEMs alike. And there are a lot of things such as resolution, views, setting car models. All of this is configurable, and we will be going in details for each of them. So this is what the input of the surround view looks like. You may have seen cars typically have these four surround view cameras that's on the front, on the sides, and one on the rear. Uh, these are the images that you get from those cameras. These are fisheye images, and you can see the field of view of these is quite large. So they almost cover everything around the car. Also, they have a lot of overlap, so that helps to build a very consistent view once we stitch them. So we will be using these surround view cameras from the EVS stack. EVS 1.1 also supports logical cameras like Chongyong explained. We will be using those and stitching them together in the surround view offering and giving you a 360 view of around the car. Next, this is what surround view looks like. There are two key things here in surround view that we offer. On the left, you see that is surround view 2D. This is sort of a bird's eye view from the top of the car, and this allows for use cases such as parking, where you want to see sort of an overlooking view of where to navigate around in a parking lot. And on the right, you see it's a 3D scene. You have a car model in the center there, and all these images stitched around to look like you're in this 3D space. And that is the second offering, which will give you sort of a view from any viewpoint in that 3D space. And that is useful for use cases such as blind spots or looking at the rear view, or any view that is useful for the driver at a particular instant. And both of these are going to be offered within surround view applications. Next, I'll go into the HAL definition. So, in order to bring this on the Android Automotive platform, we will define some common APIs that either OEMs can implement, applications can make use of. And I'll go into sort of the interfaces that we've defined for these and how to use these interfaces from a sample, from an application point of view, and this section will deep dive into that. So the first thing is I'll give an overview of what the surround view HAL basically is. Where I previously explained, the surround view HAL is a layer of APIs. It may have an implementation that either OEMs can do, or an implementation that Google will also be offering, and it is built on top of the already existing EVS camera APIs. So we get the camera frames from EVS for this, and applications are then can directly interface to this HAL layer and get the camera frames, get surround view frames similar to how camera frames are obtained. This is an overview of how the surround view HAL looks like. There are a lot of similarities with the camera, with the EVS camera stack as well. So the first thing here is the I surround view service. This is the entry point into the HAL, where there are methods to basically get a 2D or a 3D session. So application gets this service and makes call to start a particular session. Session basically implies either the 2D or the 3D pipeline is initialized and started. And so application provides an implementation of this iView stream, which is again very similar to the camera, which the application implements and gets callbacks for surround view frames or any events. This is provided to the surround view service start stream calls, which we will explore in details in the further slides. And the interface for 2D and 3D is inherited from this surround view session. And the 2D session and the 3D session interfaces themselves have additional methods, but in particular to 2D and 3D. And we will also look at those in details. So the first thing, which is the entry point for surround view, is the surround view service interface. And the few methods that it has is, firstly, the application would need a list of cameras that are being used to generate the surround view. This is defined by the OEM. And typically, these are the surround view cameras located at these fixed locations around the car. And they have an ID associated, which comes from EVS, and we provide this ID through the get camera ID function call. The next function there is the start 2D session. So like I previously explained, this interface allows you to get a 2D session that the application can then use to control and manipulate a 2D session. Similarly, the stop session is going to stop that pipeline. Same for the 3D, you get a start 3D session call and a stop 3D session call. And each of these sessions are different in a way that they have different pipelines to initialize. And so when you start a session, it is going to only initialize that particular pipeline. So let's look at what the base class or the base interface that I talked about, that both the 2D and 3D session implement. And that's the interface for the view surround view session. This has methods specifically for streaming that are common to both 2D and 3D. So the three methods that you see there are to start a stream and stop a particular stream. And like I mentioned, the start stream will take the I surround view stream interface that has been implemented by the application so that it receives callbacks. And stop stream will stop generating will stop giving these surround view frames as well as events to the application. And done with frame. So the way the implementation and the application work is the implementation keeps a stack, keeps an internal buffer of the surround view frames and waits until the application completes. And so application, once it completes its operation with a given data, with a given surround view frame, it indicates that we're done with frames. And that call allows the implementation to just clear out that buffer for that particular frame. Next, the surround view stream interface. So for this one, this is implemented by the application, and the two methods here are one to receive the surround view frames, and the second one to receive events. And so application is provides this to the start stream call and starts receiving frames or events. Frames are basically described by the SV frames descriptor, which is sort of describing what that frame has, which view ID it comes from, which we will explore in details further. And notify method will give events such as timeout events or hardware failures. And this is again very similar to how the streaming of a camera frame works. The receive, this is a sample of how an application can receive a frame. So like I mentioned, the application here is implementing that surround view stream interface, and the two methods are being implemented, and the application can then do whatever applications, whatever data processing it needs to do with these frames, or display them, for example. And in the main function call, you see that the entry point, which is the surround view service, you use the get service call and get a pointer to that service. And then further, the surround view session, 2D session interface is obtained through the start 2D session call, which is part of the surround view service interface. And so here you receive a callback of the result and the 2D session, which the application is just recording in local variables. And it creates a new surround view service callback and passes that to the start stream call. So together, so at this point, the application now should start receiving surround view frames in in its implementation, as well as events. And from here, it can do all the processing that it needs to. Next, we look into what the interfaces for 2D session and 3D session look like. Again, these extend the surround view session interfaces. So the streaming calls are already there. And each of these extend have methods for particularly 2D or 3D sessions. So for 2D, as you saw, it's an overview, like a bird's eye view, and has a specific ground coverage. And so it is important for the application to know what this map looks like, what are the length and width of this map. And so the get 2D method info provides that information. Next, the set 2D config. Like we said, we wanted the application to be able to configure things like resolution, or things like what the quality of that blending needs to be. So the 2D config allows that. So the set 2D config will take a SV2D config data structure that has information for resolution, as well as what kind of blending or what quality of that surround view is needed. And that gives a nice trade-off between performance versus quality for the application, and could be used for something specific the application needs. Similarly, the get2d config is going to return the current config. The last call is the project camera points. So for an application which is doing maybe some detections on the camera frames, like maybe it has some ultrasonics or some machine learning based detections, or just wants to know that something that is in the camera frame, where does that lie on the surround view frame? This method is helpful. So the application gives a list of points, that's the camera points, which camera it wants, where these points lie in, and it receives a set of 2D points in that surround view frame. And that can be used for overlays for as a most common use case, wherein overlays like ultrasonics can be put onto the surround view by the application. Next, the surround view 3D session. Similarly, this implements the surround view session, and these are the extra methods specific to 3D surround view. As you saw, the 3D surround view has a 3D space, and it allows you to set a view in this 3D space from which to look at. And this view could be anywhere in that space. So the set view call allows the application to set a particular position and an orientation to look at. And also, this view can be is not restricted in any way within that 3D space. Similarly, the set and get 3D config are similar to 2D, wherein resolution and the quality can be adjusted. Um, and the fourth call here is the update overlays. This is a different call wherein the overlaying is done by the implementation itself. As this is a 3D rendered pipeline, the implementation handles all the overlays that are needed. For example, if the application wants to add some virtual object within the scene or something, or would like to highlight something within that 3D surround view, this call can be used. And we will look at how the application can convey this information in the further sections. The last call, similar to 2D, the project camera to 3D surface call allows getting a list of points that the application wants from the camera space and project it onto that 3D space that the surround view generates. And to give an idea, the surround view basically generates a bowl like surface within the scene, and this point projects onto that bowl surface and provides that the coordinates of that 3D point within that space. Here again, the application can then use this 3D point to set some overlays within that scene. So I'll explore some key offerings like we discussed for Surround View 3D. One thing was the views that we talked about, and so here are some sample views that can be generated. Like you see, the left topmost one is the front view showing everything in front of the car. There is a car model in the scene showing also that is also visible. On the top right is the rear view showing something that's behind the car. And this again is useful when backing up or for some other use cases where there are objects behind. And similarly, there's a left blind spot and top view. All of these views are not fixed. They can be defined by the application as it sees fit. And we look at how an application can now set these views as it sees fit. So in the 3D surround view 3D views, we define two structures there to assist setting views. One is pose, basically setting where a view should be located and where it should be sort of looking at. And another structure called the view 3D struct. This one basically defines has a unique ID to identify that view, and has a pose like we talked about, and also has an FOV defining how wide that view should be looking. And the vertical the vertical field of view is automatically computed based on the resolution. And in the application, you see the main, here we have a vector of the 3D views setting, and which has a single element. We set the view ID to 0. We set the pose, rotation, and translation elements, the rotation being set to identity, which is defined in quaternions, and the translation being 10, 0, 0, X, Y, and Z. and horizontal FOV set to 90 degrees field of view. And then finally, we use the set view calls in the surround view 3D session to set that particular view. And as I indicated, this could be a vector of views, so the application can have a list of views that it needs and receive callbacks for all of them together. And each view then gets identified by a unique view ID that is specified in there. So now that we looked at views, the next feature within Surround View 3D is the overlays. And like we talked about, these overlays allow the application to set a particular object in the scene or highlight a particular object. And so here you see this is a view generated in 3D wherein the cars are being highlighted by these red boxes. And so we'll see how an application can set a particular overlay using the APIs. So in the surround view 3D overlays, we define a few structures here for within the HAL. So the first thing, similar to an OpenGL primitive, we define an overlay primitive, which has either triangles, which are every three vertices form a triangle, and a triangle strip where every three consecutive vertices form a triangle. And these define the geometry of that particular overlay and then are used by the implementation's rendering pipeline to generate this overlay within the scene. The next struct there is the overlay memory descriptor. This describes how that overlay is being set within the shared memory that the application is going to forward to the surround view implementation. So the overlays being large in size, application sets them to a shared memory and provides this to the surround view implementation. And this overlay memory descriptor is going to describe what that shared memory contents are. So the first thing, every object will be associated with an ID, and it has a number of vertices count. So we have a data member for that. And lastly, what primitive is being used. So this describes every object. And you could have a list of objects that you would want in the scene, like you saw each bounding box in the previous image. To do that, we have a structure overlays object, overlays data that will be set by the application in an API called the set overlays. And this has a vector of the overlay memory descriptor describing n number of objects to be overlaid in the scene. And finally, the overlay memory. This is an inbuilt data structure that basically gives a pointer to the shared memory that application has defined. And there is the layout in the comments there in that code section showing you have an ID followed by a list of vertices for each of the overlay objects. And this is how we can now look at how an application can use this code. So this is a sample application showing how to use the overlays. The application here is defining a new data structure, a custom data structure, which has position and RGBA, similar to what the layout of the shared memory looks like. In the main, we have an overlay shared memory handler. This class basically hides all the details of how a shared memory is to be allocated or mapped, and we do not show that here. So firstly, we allocate that shared memory. Next, the application defines an overlay memory descriptor. So here we have an ID set to 0, vertices count set to 3, and primitive set to triangles. So this application is going to set a single triangle as an overlay in that scene. Next, the overlay vertices is a list of the overlay vertex structure that the application has defined. And here we define the position and the RGBA values for each of those vertices. And we have three vertices here that will form a single triangle and has a red color with an alpha value of 255. And finally, we use this contiguous data to update it or map it onto the shared memory, which is done by the overlay shared memory handle update call. And finally, now that we have the overlay descriptor memory, We set this in the overlays data that needs to be that is going to be called with the update overlays call. And in the overlays data, you have to set the two data members that we set is overlays memory descriptor, which takes a vector of these objects. Since we have a single object, we just have one overlay memory descriptor here. And then the overlays memory, which is going to be the pointer to that shared memory that the application has set up, and that gets called with the update overlays. So in this way, now the scene will be set up to have a triangle in that 3D scene, and while the view changes or the user navigates, that overlay is going to remain in that scene until the application refreshes it. And that is how a simple triangle is set. But many complex structures or any advanced objects can be rendered into that scene with using this overlay. So next, like I indicated, this was the HAL definition, and we also at as Google offering, we will also be offering an implementation of this HAL, which contains all of the algorithms and all of the piping and all of the code that's necessary to take EVS frames, stitch them, blend them together, and then finally give out surround view frames, both for 2D and for 3D. And this is Google's implementation, and OEMs are free to use this out of the box, or even use this for developing their own custom surround view solutions. So, a few things that since the surround view needs a lot of information from the OEMs or things specific to the car or hardware, there are a list of things that are needed, and we this slide will go through what those things are. So, the surround view implementation that Google has these four main main files that are needed. Firstly, the surround view config XML file. This defines things such as which cameras to pick up, what internal quality details of surround view that are set for that particular hardware device, and additional such configurations pertaining to surround view 2D or 3D. Next, since you saw the surround view 3D has a model of a car inbuilt into that scene, and this model is defined by the OEM or the implementation. And so we take this from a custom, a standard 3D file like a car model OBJ and a car model MTL, which define the geometry and the materials of that model respectively. And there is an additional file, the car model config XML, that defines some parameters related to that car model, which also offers things like animations. So the surround view implementation that Google has can map a particular VHAL property, which is a property like, for example, door being opened, can be mapped to a particular object on the car model to open and close, showing realistic animations within that surround view 3D scene. And so application is gets this surround view 3D scene with the car model inbuilt into that scene, and does not need to do anything further than that. That with that, the next slide will I'll just go over what the hardware specifications are to use surround view, and this is particular to the implementation that Google has, and also I'll put some performance numbers. So in terms of hardware, the cameras that are needed are the four surround view cameras, and the EVS is what we will the HAL definition defines the EVS pointer to use these particular surround view cameras. And additionally, the calibration parameters, which are defined as part of these EVS cameras, is retrieved from EVS, and these need to be accurate for the surround view quality to look good. And that is the basic requirement. The rest is basically performance depends on how powerful the hardware is, and some numbers here. that we'd like to put. For surround view 2D, we currently have 5 frames per second for a 720p resolution output on a typical Android Automotive device hardware. And similarly, for the 3D, it's a 15 frames per second for a 720p output. And we encourage you to see. This is the first version, and we will be improving as we go ahead for this. So I'll be showing a demo of the surround view 3D, showing all these features that we talked about, such as views and overlays. So here's what you see. There's a car model in the scene, like we talked about. And as you navigate around this, the application is setting different views. And you can see the red boxes are the overlays in that scene. And the great part here is you see a complete 360 view all around the car. That concludes the demo. And thank you all, everyone, for joining. And we look forward to your questions. Thank you.